Ever stop to think about the magic trick of making something hot or cold?
Hmm.
It feels so simple. Flip a switch, light a burner, but underneath there's just this huge amount of unseen energy buzzing around, changing things.
It really is remarkable. These fundamental principles, they govern so much, but we rarely, stop to consider them.
Exactly. And that's our plan for this deep dive. We've got some excellent materials you sent over, and we're going to pull out the really key ideas, the stuff that makes it click about heat, temperature, and how matter changes state.
Yeah, the goal here is to give you a really solid understanding of thermal energy. We'll cover heat, temperature definitions, then get into things like heat capacity, latent heat, hopefully clear things up and provide some of those aha moments.
Okay, let's jump in. Heat and temperature. We use these words all the time. Sometimes, well, I know I use them interchangeably, but they're quite different concepts, aren't they?
They absolutely are. Fundamentally, heat is about the total internal energy in something. Think of all the molecules inside, jiggling around randomly, interacting. Their combined motion, their potential energy from forces between them, that's the internal energy.
Okay, the total energy.
Right. And heat, specifically, is that energy in transit. It flows, always from something hotter to something colder when they touch. And we can actually measure that flow precisely. There's a whole technique called calorimetry for that.
So heat is the total jiggling energy and it moves. How does temperature fit into that picture then?
Temperatures is more like a measure of the average kinetic energy of those molecules. How vigorous is that jiggling, on average? It tells us the thermal state, how hot or cold something feels.
Average energy.
And critically, temperature dictates the direction of that heat flow we talked about. Heat naturally flows from higher temperature to lower temperature, higher average molecular energy to lower average molecular energy.
Okay.
But here's a really important point. Two things can be the same temperature, but hold vastly different amounts of heat energy.
How so?
Well, imagine a tiny espresso cup boiling hot versus a huge swimming pool that's just lukewarm.
Okay.
The coffee molecules are moving much faster, much more energetically. On average, that's the high temperature. But the pool, even though its molecules are slower on average, has so many more molecules. The total internal energy, the heat content, is vastly greater in the pool.
Right. That makes total sense. Just sheer volume of slightly less energetic molecules adds up. So how do we measure heat? I saw joules and calories mentioned.
Correct. The standard scientific unit, the SI unit, for heat, like all energy, is the joule, symbol J.
Okay.
But you'll definitely still see the calorie, calocal, especially in older texts or when talking about food energy. Historically, 1 calorie was the heat needed to raise 1 gram of water by 1 degree Celsius.
I think I remember something about it being specific, like a certain temperature range for water.
Yes, exactly. Because water's properties aren't perfectly constant, the more precise definition is the heat needed to raise 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. That's sometimes called the 15-degree calorie.
Okay.
But for most purposes, the conversion factor is the key thing. 1 calorie is about 4.2 joules, approximately.
4.2. Got it.
And then there's the kilocalorie, nacal. That's just 1,000 calories. That's what you actually see on food labels. When they say calories, they mean kilocalories.
Okay. Good to know. Joules are standard, calories are historical, and for food, 1 cal is roughly 4.2 J. Simple enough. What about temperature units, Kelvin and Celsius?
Yep. Kelvin, K is the SI unit. It's the absolute temperature scale. Celsius, degrees C, is what we use day to day in most of the world.
And they're linked how?
It's a simple shift. To get
Yeah.
Kelvin from Celsius, you just add 273.15. So water freezes at 0 degrees C, which is 273.15 K.
In the bottom of the Kelvin scale, 0K. That's absolute zero, right? Where supposedly all molecular motion stops.
Theoretically, yes. That's equivalent to minus 273.15 degrees C. But here's a useful tip for calculations. A change in temperature is the same value on both scales.
Oh.
Yeah, a 1 degree Celsius increase is exactly the same as a 1 Kelvin increase. So if a formula uses temperature difference, you can often use either unit without converting. Makes things simpler.
That is handy. Okay, unit sorted. Now let's think about heating something up. Clearly, it takes more energy to heat, say, a big cast iron skillet than a tiny little nail, even if they're both iron. What determines how much heat is needed?
Exactly. It depends on 3 main things. First, the mass of the objects, how much stuff is there.
Makes sense. More stuff, more heat.
Right. Second, how much you want to change the temperature difference you're aiming for.
Bigger change needs more heat. Also logical.
And third, the material itself. Different substances respond differently to heat. This involves a property called specific heat capacity.
Okay, specific heat capacity. That
Yeah,
sounds important.
it really is. It sort of measures a substance's resistance to temperature change. We capture this in a formula. Q equals mc delta T.
Q equals mc delta T. Okay, break that down.
Q is the amount of heat energy transferred.
Okay.
M is the mass of the substance.
Right.
Delta T is the change in temperature.
The difference, yeah.
And C, that's the specific heat capacity. It's a value unique to each material. It tells you how much heat energy is needed to raise the temperature of 1 unit of mass, say 1 kilogram of that substance, by 1 degree Celsius or 1 Kelvin.
So if something has a high C, a high specific heat capacity, it takes a lot of energy to warm it up, and it releases a lot when it cools down.
Precisely. And conversely, low specific heat capacity means it heats up and cools down quickly with less energy transfer. Now, there's a related term, heat capacity. Without the specific, it's easy to mix them up.
Ah, okay. What's the difference?
Heat capacity, sometimes written with a capital C, is the heat needed to raise the temperature of the entire object by 1 degree. Its units are joules per Kelvin, JK.
The whole thing. Got it.
Specific heat capacity, lowercase c, is the heat needed per unit mass. Per kilogram, usually. Its units are joules per kilogram per Kelvin, JKGK.
So specific heat is about the material itself, and heat capacity is about the specific object, which depends on the material and how big it is.
You've got it. The relationship is simple. The total heat capacity, C, is just the specific heat capacity, C times the mass. C equals mc.
C equals mc. Okay. Now, I remember reading that water has a really, really high specific heat capacity compared to most things. Why is that such a big deal?
Oh, it's hugely significant. Water's specific heat capacity is around 4,200 kgK. It's much higher than, say, metals or sand. And this property has massive consequences for our planet and our technology.
Okay, what? Give me some examples.
Well, think about coastal climates.
Right.
During the day, land heats up relatively fast. Lower specific heat.
Right.
The nearby ocean absorbs the same sunlight, but because of water's high specific heat capacity, its temperature rises much more slowly.
Okay.
This temperature difference creates a pressure difference, and you get a cool sea breeze blowing inland.
Ugh, the sea breeze.
And at night, it reverses. The land cools down quickly, but the ocean holds on to its heat much longer. So you get a warmer land breeze blowing out to sea. It moderates the temperature swings near the coast.
I never realized that's the direct reason. That's fascinating. What else?
Hot water bottles. Why do they stay warm for so long?
High specific heat capacity.
Exactly. Water can store a lot of heat energy without its temperature dropping too fast. If you used, say, oil with a lower specific heat capacity, it would cool down much quicker.
Makes sense. And I guess that's also why it's used as a coolant, like in car radiators.
Perfect example. Water can absorb a large amount of waste heat from the engine without its own temperature skyrocketing. It carries that heat away efficiently.
Okay.
Another one. Farmers sometimes flood their fields if frost is forecast.
Why is that?
The water acts like a thermal blanket. As the air cools down overnight, the water releases a large amount of heat as it cools due to its high specific heat, keeping the ground and the crops just above freezing.
Clever. It acts as a heat reservoir.
Precisely. And it even applies inside living things. The high water content in plants and animals helps them maintain a stable internal temperature, buffering against external changes.
So water's high specific heat is just fundamental to, well, almost everything. What about things with low specific heat? Are they useful too?
Absolutely. Materials with low specific heat capacity heat up very quickly. Think about metals.
Right.
Good conductors of heat usually have low specific heat capacity. The base of a cooking pan, for example. You want it to get hot fast and distribute that heat evenly. A thick base helps hold the heat once it's there, but the material itself heats quickly.
Okay.
Or think about a scientific instrument called a calorimeter, which we use to measure heat changes. They're often made of copper.
Why copper?
It's a great conductor, so it reaches the same temperature as its contents quickly. But also, it has a relatively low specific heat capacity. That means the calorimeter itself doesn't steal too much of the heat being measured. It minimizes its own effect on the experiment.
Ah, I see. So you want it to respond quickly but not absorb much energy itself.
Exactly. And one last point on specific heat. It can change depending on the state of matter. Ice, liquid water, and steam all have different specific heat capacities.
Oh, interesting. Okay, so we understand heat, temperature, specific heat capacity. How do we actually measure these heat exchanges accurately? You mentioned calorimetry.
Right. Calorimetry is the technique, and a calorimeter is the device. Typically, it's a metal container, often copper, like we just discussed.
As it conducts heat well and has low specific heat.
Yes. And it's usually placed inside an insulating jacket, maybe wood or foam, to stop heat from leaking in or out from the surroundings.
Mm.
You want an isolated system as much as possible.
Yeah.
It usually has a lid, holes for a thermometer to measure the temperature, and a stirrer to make sure the contents mix well and reach a uniform temperature quickly.
And the basic idea is mixing hot and cold things inside it.
That's the core principle, often called the method of mixtures. It relies on the conservation of energy, meaning, in a perfectly insulated system, any heat lost by the hotter substance must be gained by the colder substance. Heat doesn't just disappear.
Heat lost equals heat gain.
Exactly, until they both reach the same final temperature, called thermal equilibrium.
So if I put hot metal into cold water in a calorimeter, I can figure something out by measuring the temperatures.
Precisely. Let's say you have substance 1,
Hmm.
mass mare, specific heat euro, initial temperature T, and substance 2, mass mero, specific heat euro, initial temperature T. Assume T is hotter than T.
Okay.
You mix them, and they reach a final temperature, T. The heat lost by substance 1 is mass times pseudo times TT.
Mass times specific heat times temperature drop. Makes sense.
And the heat gained by substance 2 is mass times C euro times T0.
Mass times specific heat times temperature rise.
Right. So the
Okay.
principle states,
Yeah.
if you know all the masses, the initial temperatures, the final temperature, and the specific heat of one substance, you can calculate the specific heat of the other.
Ah.
And in a real experiment, you'd also need to account for the heat gained or lost by the calorimeter itself, using its mass and specific heat in the calculation. But the principle is the same. Total heat lost equals total heat gained.
It's like balancing an energy budget.
Okay.
Now, we've talked a lot about temperature changes, but what about when things melt or boil? The temperature stays constant then, right? Even though you're adding heat.
That's absolutely right. We're moving into the realm of phase changes, transitions between solid, liquid, and gas states.
Melting, freezing, boiling.
Exactly. Melting is solid to liquid. Freezing is liquid to solid. Vaporization is liquid to gas. That includes boiling, which happens throughout the liquid, and evaporation, which happens at the surface. Condensation is gas, back to liquid. There's also sublimation, solid straight to gas, like dry ice.
Let's focus on melting. Ice at 0 degrees C. You add heat, it turns into water, also at 0 degrees C. Where does the energy go, if not into raising the temperature?
Great question. It goes into changing the structure. In a solid like ice, molecules are held in a relatively fixed, rigid lattice by intermolecular forces.
Okay.
To melt it, you need to give those molecules enough energy to partially overcome those forces, to break free from the fixed positions and move around more freely, like in a liquid. That energy input increases the potential energy associated with the molecules' positions and the forces between them, rather than their average kinetic energy, which is what temperature measures.
So the energy breaks bonds instead of speeding molecules up.
In essence, yes. It overcomes the forces holding the structure together. And for pure substances, melting and freezing happen at a specific constant temperature, the melting point or freezing point, which are the same, like 0 degrees C for water.
I've seen graphs, heating curves, showing that flat line during melting.
Exactly. That plateau graphically shows energy going in, but temperature staying constant. Now, some interesting side notes on melting. Most things expand when they melt, but water is weird ice contracts when it melts.
Which is why ice floats, right? Listens.
Precisely. And this also affects how pressure changes the melting point. For ice, increasing pressure actually lowers the melting point slightly. For most other things that expand on melting, pressure raises the melting point.
Huh. And impurities, like
Yeah.
salt on roads.
Impurities almost always lower the freezing melting point. Adding salt disrupts the formation of the ice crystal lattice, meaning it needs to be even colder for it to freeze, or it will melt at temperatures below 0 degrees C. That's how freezing mixtures work too.
Okay, so constant temperature, energy goes into breaking structure for melting. Is boiling similar? Water at 100 degrees C turns into steam at 100 degrees C.
Very similar principle. Boiling, or vaporization, requires energy input at a constant temperature, the boiling point, to overcome the intermolecular forces holding the liquid together, allowing molecules to escape into the gas phase, where they are much farther apart and move much more freely.
So again, energy increases potential energy, not kinetic energy.
Exactly. It's doing the work needed to separate the molecules against their mutual attraction. Condensation is the reverse. Gas molecules come together, form bonds to become liquid, and release that energy. Again, for a pure substance, boiling and condensation points are the same under a given pressure.
And you'd see another plateau on the heating curve at the boiling point.
You would. At 100 degrees C for water, at standard atmospheric pressure, and unlike melting, pretty much all liquids expand significantly, when they turn into gas.
Does pressure affect boiling too?
Oh, significantly. Higher pressure raises the boiling point. That's how pressure cookers work. They increase the pressure, water boils at maybe 120 degrees C instead of 100 degrees C, and food cooks faster.
Ah,
Conversely, lower pressure lowers the boiling point. At high altitudes, atmospheric pressure is lower, so water boils at, say, 90 degrees C. Makes it harder to cook things or make a proper cup of tea.
never thought about that.
And impurities in boiling water, like adding salt.
Impurities dissolved in a liquid generally raise the boiling point slightly. The dissolved particles interfere with the process of vapor escaping. Okay, so for both melting and boiling, there's this energy transfer happening at a constant temperature. This must be the latent heat concept.
Precisely. Latent heat is the energy absorbed or released per unit mass during a phase change at constant temperature. Latent means hidden, because you don't see it as a temperature change.
Per unit mass, so there's a specific value for each substance in each transition.
Yes, we talk about the specific latent heat, symbol L. It's the total heat Q divided by the mass M changing phase. L equals QM. The SI unit is joules per kilogram, JKG. You might also see calories per gram, calg, or kcalg.
And there's one for melting, freezing, and one for boiling, condensing.
Correct. We call them the specific latent heat of fusion for melting, freezing, and the specific latent heat of vaporization for boiling, condensing.
Let's take ice. What's its specific latent heat of fusion?
For ice melting into water at 0 degrees C, it's quite large, about 336,000 joules per kilogram.
Wow.
Or, in the older units, it's about 80 calories per gram. Think about that. It takes 80 calories to melt 1 gram of ice at 0 degrees C into water at 0 degrees C.
And how much heat does it take to warm water?
Well, the specific heat capacity of water is 1 calorie per gram per degree Celsius. So the energy needed to melt the ice is the same amount of energy needed to raise the temperature of that same gram of water all the way from 0 degrees C up to 80 degrees C.
That really puts it in perspective. So 0 degrees C water has way more internal energy locked away in it than 0 degrees C ice does.
Exactly right. That latent heat absorbed during melting is stored as increased potential energy in the liquid state.
And we already touched on the kinetic model explanation. Energy goes into breaking bonds, increasing potential energy, while kinetic energy, temperature, stays the same.
Precisely. The molecules get further apart, overcoming those attractive forces.
So just like high specific heat capacity had big consequences, does this high latent heat of fusion for ice also matter in the real world?
Immensely. Think about snow on mountains in spring.
Okay.
Because it takes so much energy to melt ice, high latent heat of fusion, the snow melts relatively slowly, even when the air temperature is above freezing. This prevents catastrophic flooding from sudden meltwater release.
Ah, gradual release. Makes sense.
Or consider lakes and ponds in winter. A huge amount of heat has to be extracted from the water just to freeze the top layer because of latent heat.
Right.
And then ice itself is actually a pretty good insulator, so once a layer forms, it slows down the freezing of the water underneath, protecting aquatic life. The entire lake doesn't easily freeze solid.
That's crucial for those ecosystems.
Definitely. And on a smaller scale, why does ice cool your drink so much better than just adding the same amount of ice-cold water?
Because the ice has to melt first.
Exactly. As it melts, it has to absorb that significant latent heat of fusion from your drink, cooling it much more effectively than water that's already liquid at 0 degrees C, which can only cool the drink by rising in temperature itself.
Okay, that makes perfect sense now.
And it's why the surroundings feel cold when ice melts. It's actively sucking heat energy out of the environment to fuel the phase change. Same reason it feels colder after a hailstorm. The melting hail absorbs a lot of heat.
It really ties everything together, this constant exchange of energy, sometimes changing temperature, sometimes changing state. It's quite elegant, actually.
It really is. Understanding these core ideas, heat, temperature, specific heat, latent heat, calorimetry, gives you such a powerful framework for understanding how the physical world works, from the microscopic to the macroscopic.
Okay, wow, we covered a lot there. We went from defining heat and temperature, making sure we knew the difference, looked at the units, then specific heat capacity, how different materials handle heat.
And calorimetry for measuring it.
Right, heat lost equals heat gained. And then the whole fascinating world of phase changes, constant temperature, and that hidden latent heat energy. It definitely makes you look at everyday things differently.
Absolutely. Heating water for tea, the weather patterns, why ice cubes work so well. It's all rooted in these principles.
And thinking bigger, These concepts are fundamental to so much technology and, well, understanding our planet too, right? Like climate modeling must heavily involve this stuff.
Oh, absolutely. Energy balance, phase changes of water in the atmosphere and oceans, it's all core thermodynamics. Understanding heat transfer and latent heat is crucial for predicting climate dynamics, designing efficient engines, developing new materials. The list goes on.
So maybe a final thought for everyone listening. Next time you see ice melting or water boiling or feel that sea breeze, just take a second to think about the energy flowing, the molecules rearranging. What other things in your daily life are governed by these same powerful principles?
It's a great question. How does thermal energy shape the natural processes or the technologies we rely on in ways we haven't even considered yet?
Definitely food for thought. Well, this deep dive has certainly illuminated that hidden world of thermal energy for me. Thanks for joining us as we unpacked all that.
My pleasure.
Until our next exploration, keep asking those questions.